In the last lecture, we discussed what simultaneous equation models are. So, we gave a very brief account of what the model is like structurally, and we gave a little bit of idea of what the difficulties are when we are treating the simultaneous equation models. One of the major problems that arises in simultaneous equations is the problem of identification. If you remember the model that we wrote the other day, you will see that the equations look similar except for the suffixes in the coefficients, but then these are unknown coefficients and it is very difficult to really interpret what they are. So, I can always call beta 1 2 as beta 1 1 etc., and then the equations will look similar. So, if all the G equations look similar, then how do we identify these equations separately? That would be the problem of identification, and what we will do in today's lecture would be to look in great details about the identification problem. In the study of simultaneous equation models, we can broadly look into two different aspects. The first of this is the identification problem, and the second is the methods of estimation that we use to estimate the parameters of the model. Now, what is the identification problem and why is it so important? Now, given a set of equations, it is necessary to know if the parameters of a particular equation can be meaningfully estimated. The equation is then said to be identified. Why do we say meaningfully estimated? That is because, as we saw in the previous lecture, that we can have a slope which may stand for the demand function, which may stand for the supply function, or maybe a convex combination of the two. So, in that case the slope does not meaningfully estimate any one of the single equation, and hence we need to first identify the equation properly so that we can relate the slope to a particular equation. Once we can do that, and when we have a set of G equations, we only can estimate the parameters of the identified equations, because these are the parameters which can be meaningfully estimated. So, identification comes before you actually go for estimation. You can estimate the parameters, but if you do not have identification, the interpretations would go absolutely wrong. Let us go back to the example we had been looking at in the last class. We had the demand function Qt as a linear function of Pt, and similarly the supply function Qt as a linear function of Pt again. What we would be interested to do would be to estimate the parameters alpha naught alpha 1 and beta naught beta 1. As you remember, if I take the convex combination of the demand and the supply function, then it turns out to be a linear function of Pt again, and it looks similar to the demand and the supply functions. And we saw that alpha 1 hat, beta 1 hat, gamma 1 hat, given the same set of observations Pt and Qt for say n observations, turns out to be the same. So, once we get this slope, it can stand for alpha 1, it can stand for beta 1, it can stand for gamma 1. Similarly, for the intercept alpha naught, beta naught and gamma naught, all three would be given by the same intercept q bar minus slope into p bar. In that case, we say that the parameters cannot be meaningfully estimated. Mind you, the economists would tell you that alpha 1 hat should be negative in most cases, beta 1 hat should be positive, but there are no hard and fast statistical guidelines for this. So, we can just guess that if it is a negative value, we will be looking at the demand function. If it is a positive value, we can be looking at the supply function. but there are exceptions when the reverse happens, and hence we are not very sure as to what the slope and the intercept stand for, and we cannot say that these two equations can be meaningfully estimated. So, we have a problem of identification of both of these equations. Now, let us look at another case. In this case, as before, we have the supply function Qt as a function, linear function of Pt, but the demand is now a function of both price and the taste or habits of individuals, Ht. So, we have an extra variable in the demand function. What happens if we take a convex combination of these two? The convex combination would be a function of both price and habits. This is because if we multiply the first equation by lambda and the second by 1 minus lambda, then obviously there would be a coefficient for Ht coming in from the first equation, and therefore we would have gamma 2 Ht in the convex combination. So, now you see that the demand function and the convex combination looks similar, but not the supply function. So, what happens if we run a regression of Q on P and H? In this case, if the coefficient of H is insignificant, that is, if the coefficient turns out to be near about 0, then we can say that it is the supply function, because the supply function does not have H really means that it has an H with a 0 coefficient. So, an insignificant Ht would actually identify the supply function, but not so for the demand, because the demand function, if the coefficient is significant, then we cannot say it is a demand function, because it can still be the convex combination of the demand and the supply function. So, in this case we say that the supply function is identified, but not the demand function. This is interesting, because what we see is that the supply function has one variable less and hence becomes identified. We will come back to this later. Let us look at another problem. In this case, we have an additional variable in the supply function as well. This is the rainfall RT. So, there is one dependent variable common to both, that is the price, one variable which is there in the demand function only, that is Ht, and one variable which is in the supply function only, that is RT. And the convex combination would have both Ht RT along with Pt. Now, if we run the regression of Q on Pt, Ht and RT, then several things can happen. And what will be the conclusions drawn from this? Firstly, if the coefficient of Ht is insignificant, then it must be the supply function, because the supply function has a 0 coefficient for Ht, and insignificance would mean that the coefficient is very close to 0. So, the supply function would be identified if Ht is insignificant. Similarly, the demand function is identified if the coefficient of RT is insignificant, because RT is absent in the demand function, and the absence of RT in the demand function would make it identified. So, what is happening? Let us look at what happened. The illustration shows that an equation is identified if it has missing variables. What does this mean? Put in another way, an equation is identified if it has some 0 coefficients. If you have 0 coefficient, it really means that the variable would not enter the equation. So, that is, we have a case of missing variables. So, either you say it is a missing variable, or you say that the variable is there, but it has a 0 coefficient. Why do you put it the other way around? This is because when you say it has a 0 coefficient, what you really mean is that you are putting a restriction on the coefficient, you are making it 0, and we will see that these restrictions play a large part in the identification problem. Of course, if a variable is missing from all the equation, it does not help in the identification. Obviously, if it is missing from each of the equations, then the whole variable goes out actually. So, it does not, you just have g minus 1 variable or maybe k minus 1 variables, exogenous variables, and it does not help in the identification. So, it must be missing in some and present in some, so that we can identify some of the equations with respect to the other equations. But apart from this mix up, what other problems does non-identification create? So, we see that identification mixes up the equations, we do not know what is happening where. But is there any other problem related to this, particularly with respect to estimation? Let us see. But to do that, let us first go back to the structural form equations. So, we will look at the structural model. This is what we have defined before. We have by plus gamma x is equal to y. B is a G by G matrix of the betas, the coefficients of the G endogenous variables y. Gamma is a G by K matrix of gammas, which are the coefficients of the exogenous variables x1, x2, xk, and U is the vector of disturbances. B and gamma are referred to as the structural parameters. Now, the structural form equations are not suitable for estimation. We cannot directly estimate from this, because even if identification was possible, the endogenous variables yj's are correlated to the disturbances uj's, leading to inconsistent estimators. Remember what we saw in the last lecture, that y1 can be written in terms of y2 etc. and the x's and the error, and we saw that y2 would be related to the errors, or similarly for y3 would be related to the errors. So, all the endogenous variables on the right hand side would be related to the errors, and hence this would cause inconsistency in the estimators. So, we have a problem. How to get over this problem? Let us see. So, what is done usually is that instead of the structural form equations, we look at what are referred to as the reduced form equations. What are reduced form equations? We have beta y plus gamma x is equal to u, and remember that B is a G by G non-singular matrix. So, what we can do is, we can always invert this B, and hence we can write y is equal to minus B inverse gamma x plus B inverse u. Once we do this, we have the reduced form equations. We write y equal to pi x plus v, where of course v is the second term on the right hand side, B inverse u. What is pi? We will call pi the reduced form parameters. Now, this is a G by K matrix of the form pi equal to pi 1 1, pi 1 2, pi 1 k, etc. But then what is pi? Pi is related to the structural parameters, as pi is equal to minus B inverse gamma, or if you just bring B, revert B back again, it is B pi plus gamma is equal to 0. So, there is a relationship between the structural and the reduced form equations. Now, why do you go for the reduced form equations? What are the implications of this reduced form equations? Firstly, the reduced form expresses the variables y, which are the endogenous variables, solely in terms of the exogenous variables. So, on the left hand side we just have y, on the right hand side we have pi into x plus the error v. Remember, x is uncorrelated to u, and hence x must be uncorrelated to v. So, what we can do is, we can use the least squares on the reduced form and this will not lead to inconsistent estimators because x is now uncorrelated to the error. So, the problem of inconsistency would not happen if we are looking at the reduced form equations and applying the ordinary least squares. The only problem is previously we had g square plus gk parameters. So, the structural equation had two components, b which had g square elements and gamma which had gk elements. So, there were g square plus g plus k elements. On the other hand, pi is a g by k dimensional matrix and hence has gk parameters. So, there are a reduction in the number of parameters, and we will see what the problem this creates. Now, let us have a revisitation of the identification problem. Although reduced form parameters, as we just saw, can be consistently estimated, the econometricians will not be interested in them. Why not? They will want estimates of the structural form parameters which relates to their economic models. Mind you, the structural equations are the equations that the econometricians or economists actually build up based on economic theory. We have turned this into a reduced form model because as statistician we find that there are problems of inconsistencies because of endogenous variables present, but that will not actually satisfy the econometricians. They are not interested in the reduced form parameters, they are more interested, because interpreting those would be difficult for them, they are interested in the structural form parameters which they can interpret, but we cannot get those, we can only get the reduced form parameters. So, what we need to do is we need to estimate the structural form parameters from the reduced form parameters. The question is, can we do that? And how would this problem relate to the identification problem that we had been talking about? Let us see this. Let us see this through an example. Let us take g equal to 2 and k equal to 2. That is, there are two endogenous and two exogenous variables. So, the first variable equation is y1 is alpha naught plus alpha 1 y2 plus alpha 2 x1 plus alpha 3 x3 plus e1. And the second equation is y2 is beta naught plus beta 1 y1 plus beta 2 x1 plus beta 3 x2 plus y2. So, y1 is the response in the first and the explanatory variable in the second, y2 is the response in the second and the explanatory variable in the first. Now, in the reduced form the equations become y1 is equal to this expression in 3 and y2 is the expression in 4. How did we get this? This is simple. Take y2 from 2 and substitute it in place of y2 on the right hand side in 1, and then you solve for y1, because once you substitute for y2 it becomes a function of y1 x1 x2, and then you simplify and write it in terms of y1. So, you get it the equation 3. Similarly, take y1 from the first equation, substitute that on the right hand side of the second equation, and then simplify and you get equation 4, which is y2 in terms of x1 and x2. So, now you see that 3 and 4 simply has an intercept and two terms which are coefficients primarily, which involves only x1 and x2, the exogenous variables. So, the right hand side of 3 and 4 are independent of the endogenous variables y1 and y2. Now, if we now regress y1 on x1 and x2, we look at the first of the two equations 3 and 4, the estimates of the reduced form parameters of equation 3 can be obtained as pi 1 hat naught, that is the intercept, pi 1 1 hat is the coefficient of x1, and pi 1 2 hat is the coefficient of x 2. So, if you run the regression, we get these three, the intercept and the two slopes, the coefficients of x 1 and x 2. Similarly, if you look at equation 4 and run a regression of y 2 on x 1 and x 2, then we get the slope again pi 2, the intercept pi 2 naught hat, the first slope as pi 2 1 hat and the slope of x 2 as pi 2 2 hat. So, we get those two sets of equations. There are 6 equations involving how many parameters? There is alpha naught, alpha 1 and alpha 2, alpha 3, 4 parameters from the first set, and beta naught, beta 1, beta 2, beta 3 from the second set. 6 equation in 8 parameters. Can we solve them? Unfortunately, no. So, if we cannot solve them, we cannot extract the structural form parameters alpha naught, alpha 1, alpha 2, alpha 3 and beta naught, beta 1, beta 2, beta 3 from the reduced form parameters of pi hats. You can try this and see that this cannot be solved. So, we have a problem of identification in this case and we cannot estimate the parameters. Let us look at a slightly different problem. Suppose in these two equations alpha 3 was equal to 0. Remember, alpha 3 is the coefficient of x 2 in the first model. So, first model now only has y 2 and x 1 as the coefficients or the two explanatory variables with the given coefficients. Now, if alpha 3 is equal to 0, then we know that the first equation is identified, but not the second equation. We have seen that if you have a missing variable, then that equation would be identified. The missing variable is in the first equation, hence it is identified, but not the other equation. Now, what happens to the estimates? If we look at the estimates now, they would be a little bit more simplified. So, we again can estimate pi 1 hat 1 naught hat, pi 1 1 hat and pi 1 2 hat from the first reduced form equation with pi 1 naught as the intercept, pi 1 1 as the coefficient of x 1 and pi 1 2 as the coefficient of x 2. Similarly, we can get the estimates for the second set of reduced form parameters pi 2 naught, pi 2 1 and pi 2 2. Now, if we look at this, what we can see is that if I take the ratio of pi 1 2 hat by pi 2 2 hat, ratio of the third component in both cases, what we get is alpha 1 hat. The beta 3 by 1 minus alpha 1 beta 1 cancels off and we are left with alpha 1, and hence we get a solution for alpha 1 hat. Similarly, a little algebra would show you that we can solve for alpha 2 hat and alpha naught hat as well. Problem is, we still cannot solve for beta naught, beta 1, beta 2 and beta 3. So, what happens here is that the first equation parameters are estimable, but not the second equation parameters. So, how is identification related to this? So, what we see is that if the equation is identified, then its parameters can be estimated. If it is not identified, then the parameters cannot be estimated. What if both alpha 2 and alpha 3 are equal to 0? Again, these are in the first equation. So, what we are saying is that the first equation y 1 depends only on y 2 and there is no x 1 and x 2 in this. In this case, of course, the first equation is identified, but the estimates becomes a little bit even simpler. So, we have pi 1 naught, pi 1 1 and pi 1 2 from the first equation, and from the second equation of the reduced form we have pi 2 naught, pi 2 1 and pi 2 2. Then what happens? There are two things that happen. So, there is an OR here. If you look at the second component in both, so if we write pi 1 1 hat by pi 2 1 hat, we get alpha 1 hat. So, alpha 1 hat can be estimated as pi 1 hat by pi 2 hat. But then if you look at the third components, pi 1 2 hat and pi 2 2 hat, the ratio of these two also gives you alpha 1 hat. So, we can have two different estimates of alpha 1 hat, and similarly obviously corresponding to this we will have two different estimates for alpha naught also. So, in this case we say that there are multiple solutions for this first equation, and hence the first equation is over identified. We have more than we actually required. Unfortunately, again in this case the second equation does not have any restrictions, and hence the second equation is not identified, and also we can see from the estimates we cannot solve for beta naught, beta 1, beta 2 and beta 3. So, the second equation is still unsolvable. So, you see that there is a relationship between identification and estimability of the parameters. If an equation is not identified, then we cannot estimate its parameters. The second problem is, and if an equation is exactly identified, then we get a unique solution to the parameters. And if it is over identified, that means we have more restrictions than that is required, then what we have is a case of multiple solutions, and again we might have a problem here if we have too many solutions. We will look at the identification problem in more details in relation to this and how we actually identify the equations. In today's lecture, we saw what identification problem is in a simultaneous equation models. We saw the difficulty it creates and what are the problems related to it. Also, we saw that identification causes problems in the estimation of the parameters of the models. What we will do in the next classes is to elaborate on how to tackle the identification problem, or how to identify an equation before you can think of estimating the parameters of those models.